equals plus 7. So the assigned octet number for manganese, iron is plus 7. Plus 7 plus 2 is what I'm trying to get to. Okay? Now, to do this, okay, you need a certain number of electrons, right? So the charge is the same. Now, over here is plus 7, the charge over here is plus 2. Don't worry about the wires that we have added this here. So obviously it's off right now. I'll do it later. So this is what I get right now. Okay? This goes to that. You get the same type of charges on the manganese. I don't care about the oxygen. Okay? So that's not doing the redox for us, or the redox for us. Not doing anything. The manganese is doing it. Okay? Plus 7, plus 2, and one of the most charges over here to be the same. What do I add over here? How many electrons? 5. Okay, so 5 electrons, because 7 plus minus 5 equals plus 2. Okay? That's why I have the plus 5 here. We add 5 electrons on the reactant side. Since the manganese on the permanganate ion is gaining those electrons, then we call this reaction what? Reduction reaction. So that's what's gaining the electrons. It's not the oxygen is doing, it's the manganese. Okay? Alright. Now, the idea is this though, I want an overall reaction. We're doing a separate reaction right now, the way it's written. I want an overall one. That way I can balance it. Okay? To do this, we still have to satisfy the law of conservation of matter. Okay? Right now, this guy over here, okay, is showing me the fact that 1 electron was released. Okay? Or produced. This guy, however, is going to take how many? 5 electrons. But can that happen? Can you get just one, give up 1 electron and get 5 on its own? No, I can't. Therefore, it has to have the same number of electrons. What you do now is you multiply some number with the same number of electrons from the product of the reactants. You get a number, the number of electrons should cancel out. It should equal to 0. Because electronically, you use them all, right? It makes this much. I'm going to use them all. So let them transfer should equal to 0. That's why they don't show up at the end in the reaction. This is 1 right now, here's 5. If I'm going to multiply the top reaction by 5. Now, so I have 5 times 1 is 5. 5 times 1, of course, is 5. Iron plus 3. 5 times 1, of course, is 5. Iron, 5 electrons. There we go. Okay. Now, this guy though, the other reaction. See how you have the oxygen here? Okay. But you see how over here there's no oxygen present, right? What you end up doing is still what we're going to go over on Tuesday. Okay. So the next thing you have to do is first thing you should do, okay, you should balance everything here except for oxygen and hydrogen. So we'll do that first. Okay. So iron, there's 1 and 1, manganese is 1 and 1, so we're done. Okay. We balance the electrons, sheet 5 and 5 here. Now let's balance everything else now. Okay. For example, okay, I have how many oxygens over here? 4. There's 0 over here. The rule says to then add water to the side because I have that number of oxygen. That's how you make it up. In this case, on the broader side, I add how many water molecules? 4. 4 times 1 is 4. So that's balanced. Okay? Now, I have hydrogens. I have how many of them? 8 on the product side. How many do you have over here? 0. So what I'm going to do is I'm going to add protons now. The next step. So I need how many over here? 8 of them. And since I have the protons now, H pluses, remember the definition of Lloyd-Bronson, right? A proton is considered a what when it donates protons? What is it? We talked about it.
Acid?
It's an acid. This is why this iron analysis by reapplication is done in an acidic solution. And that's what that section 4.10 does. You can balance an oxidation reduction reaction in either acidic or basic solution. And having the protons present over here somewhere, that's acidic. If you want to get rid of it, that's the next part. So we add water, and then you end up with hydroxide ions. And it's basic. That's it. So here you go. So when I have this, so this guy over here makes it acidic. And it's like we're going to be dealing with. We're going to be dealing with phosphoric, sulfuric acid. Okay? So inside this guy, when you're ready to titrate, not yet, but when you're ready to titrate, you're going to dissolve the iron to ammonium sulfate with the 6 water molecules, hydrates, with 50 milliliters of sulfuric acid. It's coming in a safe solution. Okay? But then we're going to do something with phosphoric acid when I talk about the hydrogen and whatnot and the other parts. Alright, so there you go. So that means it's acidic. Okay, so now, electrons. Well, there's 5 electrons that was lost. Okay, because it came from the iron plus 2. Meaning how many moles this thing? 5. For every 5, you give up 5 electrons. This guy over here takes up those 5 electrons that it loses from here. So at the end, what I do is this, just cast them out. Okay? Now, at the end, I want to bring it all together to get an overall reaction. Okay? So I draw the line here, and so we're going to prepare all the reactions and all the products down. To get an overall reaction. So here I have iron plus 2. I have my 8 protons. I have a manganese ion. It goes to manganese ion, water, plus the 5 moles of the iron plus 3. Okay? Now, the last thing to do, of course, is to check to make sure this is balanced. Okay? Both the number of species, atoms to the left and equal to the right. Also, the overall charge on the reactive side must be equal to the charge on the product side. Have to be the same. So check it out. How many iron on the left? 5. How many on the right? 5. So that's balanced. How many hydrogens? 80. How many on the right? 8. 4 times 2 is 8. How many manganese on the left? How many here? 1. Oxygens? 4. And this one? 4. Alright, now the charge. Yeah, 5 times 2 is what? 10. Plus 10. 8 times 1 plus 8. 1 times minus 1. Minus 1. That equals to what? Plus 17. That's the reactant side charge. And go over on the product side. Well, 1 times 2 plus 2 plus 2. 4 times 0. If I have no charge here, 0. It's just 0. Don't worry about neutral molecules. 5 times 3 though is 15 plus 15. You add it up and you get 17. So they're balanced. This is how you do this thing. Okay? Some very complex ones. So I'll give you an answer for it. Okay? Because balancing the oxidation and reaction. So now, the overall reaction formula is we need 5 moles of iron plus 2, and that comes from your sample. We react with 8 moles of the acid plus just 1 mole of potassium manganese. That makes 1 mole of the manganese ion plus 2, 4 moles of water, and of course 5 moles of iron plus 3. That's it. That is the biochemical reaction. And that's what you guys need in order to answer all those calculations it says to do. Okay? That's why I said include that in your pre-lab, and it came from that page 164, a very bottom, step 5. Okay? Alright, any questions about this so far? Alright, so here's the reaction. This is how we break it down. The purpose of this overall experiment is to calculate what though? Mass percent of the iron solid in this case. Okay? We do the same thing we did before, right? A percentage is nothing but what? Part over whole times 100. Okay? So in this case, remember, your sample contains iron. Okay? It's iron plus 2. Okay, it got oxidized, it's fine. And it was reduced. Iron plus 2, ammonium sulfate, and it has water. 6 moles of water for every molecule of it. Alright, we have that. That's the total amount here. It has all this stuff in it. You guys just want, of course, it's the parts. In this case, it's what's going to be the part in this case. Huh? Just throw it away. I want to get the mass percent of iron. I know my total, all that stuff. What's the part going to be? Last time, remember acetic acid and acetoacetic acid? Right? It was the amount of acetic acid that was in the container that Dave had divided by the what? Total.